Actually, I want to mention two things real quick while still fresh in my mind. So one thing is the difference between image and camera frame. It's a small detail, but a pretty important one. We'll get into details of this in the future. So image frame it begins, so if this is the image, right, usually, and this is the center of the image, so usually it begins in the top left, so the 0, 0 is in the top left of the image, and then the x goes right, first coordinate goes right, and then the second coordinate goes left, and 1 unit is 1 pixel. This is the usual way to think about it. And then camera frame, it has similar alignment of the so the axes point in similar directions, but there's one very important difference, and I'm already drawing it incorrectly. So if the image is like this, then the camera frame begins in the middle of the picture, and still x-axis points right, and then y-axis points down, and then z actually points away from us into the word. So this is the common way to define the camera frame, at least in my word. Again, it's only a convention, right? But that's how I'm used to think about it, and that's how I've seen people think about it. And then the second thing is, so I just want to clarify a little bit still about rotations in 3D. So first is Euler angles. So Euler angles is yaw, pitch, and roll, and I don't know how to yes, basically I just have stupid mnemonics, right? So pitch is like pitch your nose down or pitch your nose up, right? So this is sort of like nose down, nose up, nose. So in other words, if I have like a coordinate system, and this is like x, y, z, and y is pointing away from me, so this is rotation around x-axis. So this is x-axis, right? And then roll is this. So roll left, roll right, like I don't know, like a cat on carpet or something. So this is around y, and then the only thing that's left is like the z. So this must be the yaw, right? I mean, those are like super silly heuristics, but that's how they work for me. And I remember the side of the rotation purely based on the so you know, positive angles go sort of this way, right? So it's like rotation goes this direction. So that's kind of silly, right? But that's how I remember it. And then there's like another convention, right? So of expressing the arbitrary rotation in 3D, and also just like proving all of this is kind of like complex and long and so on. But basically you could have like, okay, so here's a coordinate system, right? And then you just make like an arbitrary vector. Let's say it points like, it sort of points like a little bit to the top, a little bit to the right, right? And then like you take a unit vector against, so let's say this is some kind of like a vector, right? So it's called v. Maybe it has coordinates 7, 4, 1. And then, so this is v. Then you normalize v. So square root of 7 plus 4 squared plus 1 equals something, I don't know how much it is, like square root of like what, 66, which is like I don't know how much that is. That's K. So it's like you have 7 caves and then 4 cave and then 1 cave. So this is sort of your axis of rotation, and then you can encode in V. So this is how much you rotate, and this is like a really efficient way of just using free floats to encode rotation. And then yeah, some people use this, and then there's a way to get the rotation matrix from this and vice versa, go from rotation matrix to this, because all you need is 3 numbers. So 3D rotations is a 3-dimensional space. And then there's a thing called gimbal lock that's about Euler angles, and this sort of shows why Euler angles are not sufficient to be used in its own for the representation of the all rotations, right? And yeah, this one I just keep forgetting it, but basically it's something, I don't know, just like let's read it together in Wikipedia. It was something like that: if you do one, it's not, it should be the same as the other, but it's not. Oh, it's loss of 1 degree of Freeman free gimbal that occurs, yeah. Okay. Oh. Rotation in 3D space can be represented numerically with matrices. Okay, so B. Okay, this is this. Multiply it. The last common, yeah. So it's possible to imagine an aeroplane rotated by the above mentioned Euler angles. The first angle, alpha, is the pitch. The yaw. Oh, I see, right? So let's come to the thing. So we have the airplane. Oh, I'm bad at drawing airplanes. Okay. This is the worst airplane ever, right? Okay, so this is sort of the pitch, right? So the pitch is positive. And then we do the yaw. So the yaw, we set yaw equals 90 degrees. So bird's eye view. So this was like this, and now we set the airplane to point in this direction. And then turns out that now our roll will set our pitch. That's it. That's the gimbal lock. Yeah. So it makes the Euler angles unsuited for practical applications. So yeah, just something that I had to mention about those two. That's it. See you later.